Hello everyone, this is Professor Roman. Welcome to the 15th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to continue our discussion of binary relations on sets by first looking at some of their basic properties, or I should say properties that a relation may or may not possess. A relation, binary relation R on a set A is reflexive if A are A for all A in the underlying set. In other words, if every element is related to itself. A relation is irreflexive if no element is related to itself. A relation is symmetric if ARB implies BRA for all elements A and B in the underlying set. A relation is antisymmetric if ARB and BRA implies A equals B. So if A and B are related in both directions, A related to B, B related to A, then A and B have to be the same element or equal. R is asymmetric if ARB implies B not RA. So if A is related to B, then B is not related to A. And finally, R is transitive if A R B and B R C implies A R C. I know it's a lot to remember, to memorize if you will. I think most of these are pretty straightforward. It's this group related to symmetry that can get confusing, in particular the difference between anti-symmetric and asymmetric. It might help to think about the prefix A on a word. Amoral means not moral. What are some other examples? Atypical means not typical. Asymmetric means not symmetric. So if that helps, good. And then anti-symmetry is the other one. Okay. But ultimately, you just have to deal with these terms. And the more you use them, the more comfortable they will become. One of the best ways to get a feel for these properties is to consider their effect on a graph of a binary relation on a finite set, on the directed graph of the relation. So here is a list, and it's something you should dwell on until it seems quite reasonable to you. A relation is reflexive if and only if its graph has a loop at each vertex, and irreflexive if it has no loops at all. A relation is symmetric if and only if whenever there's an arc from A to B, there is also an arc from B to A. A relation is anti-symmetric if and only if whenever there's an arc from A to B and an arc from B to A, then A and B are the same vertex. A relation is asymmetric if and only if there is at most one arc between any two distinct vertices. A relation is transitive if and only if whenever there's an arc from A to B and an arc from B to C, then there's also an arc from A to C that completes the triangle. Now the difference between between anti-symmetry and asymmetry is a little bit subtle, and it has to do with and only with loops. And I'm going to talk about that more in a little while, but as practice, see if you can sort out that difference. I've given you a hint about loops. See if you can get a firm grasp on the difference between asymmetry and anti-symmetry. Okay? I mean, the only way you'll get comfortable with these properties is if you think about them. This graph is the graph of a relation on the set 1, 2, 3. It is reflexive because there's a loop at each node. It's transitive, but it is not symmetric, it's not anti-symmetric, it's not asymmetric. To see that it's transitive takes a little work. Fortunately, this is a small graph. If it was a large graph, it would be very, very difficult. But what we have to do here is make a list of pairs of the form ARB, BRC. So 1 related to 2, 2 related to 3. Okay. 2 related to 1, which is related to 3. And you'll have to convince yourself those are the only 2 directed paths of length 2. Okay. And you need to check in each case to make sure that, well, A, R, C. So in the first case, 1 has to be related to 3, which it is. And in the second case, 2 has to be related to 3, which it is. So that is transitivity. The hard part is really convincing yourself these are the only 2 arc paths. So that's all you need to check. Okay. To see that this graph is, the relation of this graph is not symmetric, well, we have 1 related to 3, but 3 is not related to 1. It's not anti-symmetric because 1 is related to 2 and 2 is related to 1, and yet 1 and 2 are different. And it's not asymmetric because 1 is related to 2. Asymmetry would imply 2 is not related to 1, and that's false. Symmetry is really a key property of binary relations. Many important binary relations are symmetric. Unfortunately, many are anti-symmetric, but that's the way it is. When a relation is symmetric, then ARB implies BRA. And that means all we have to say is that A and B are related. We don't have to specify a direction because related means related in both directions when the relation is symmetric. Okay. And that's a great simplification, really. The properties described in the previous definition are not independent. There are some relationships between them. And here are 2 very important ones. A binary relation R is asymmetric if and only if it's both antisymmetric and irreflexive. Those are equivalent: asymmetry, antisymmetry, and irreflexivity. So herein you can see a relationship between asymmetry and antisymmetry. What does irreflexive mean? No loops. So that refers to the hint I gave you earlier. Also, if R is transitive and irreflexive, it will be asymmetric. So here's a summary. You don't have to memorize this, partly because if you need these relationships, you can look them up or you can sort them out yourself. The proofs are not that difficult. Okay. And so as good practice, I would strongly urge you to try to prove these yourself. You see my proofs. The second one in particular is very short. I would strongly suggest you work on that yourself. What happens if a relation is both symmetric and anti-symmetric? Well, this is another thing you can work out once you get comfortable with these terms. Symmetry means ARB implies BRA, but if ARB and BRA, then anti-symmetry implies A equals B. So if we start with ARB, the symmetry gives us BRA, and then the anti-symmetry will give us A equals B. In other words, if two elements are related, they're the same element. But that's not an if and only if. So a relation that is both symmetric and anti-symmetric must be a subset of the equality relation. It doesn't have to be full equality. Okay. I've talked about equality at some length earlier. However equality is defined on a given set, it should be reflexive, symmetric, and transitive. And the reason is that these are the properties that really capture the essence of equality. Everything should be equal to itself. If A is equal to B, B should be equal to A. Otherwise, it's chaos. And if A is equal to B and B is equal to C, all three are equal. Okay. So if you are defining a new set of mathematical objects and you decide to define equality, if you don't define it in such a way that it is reflexive, symmetric, and transitive, you're going to get a lot of nasty letters. Okay. Equality of polynomial functions is reflexive, symmetric, and transitive. Equality of formal polynomials, identicality, or formal words is reflexive, symmetric, and transitive. The inequality relation less than or equal to on R is reflexive. Every real number is less than or equal to itself. It's also anti-symmetric, since A less than or equal to B and B less than or equal to A imply that A equals B, and it's transitive. Strict inequality, however, is not reflexive. A is not strictly less than itself. It's not symmetric. It's not anti-symmetric, but it is asymmetric. A less than B implies B is not less than A. And strict inequality is transitive. Okay. The relation of congruence mod K is reflexive, symmetric, and transitive. It's reflexive since A is congruent to itself mod K. The difference is 0. That's divisible by K. It's symmetric because A congruent to B mod K means K divides the difference A minus B. It also therefore divides B minus A, and so B is congruent to A mod K. And I'm going to leave it for you to check transitivity. That's the hardest of the three. So congruence mod K is a candidate for equality under certain well, it's a candidate, and it is in fact taken as equality under some circumstances. It's never quite said that way, but it's implied that way. And we'll get into that actually when we discuss what are called equivalence relations later on. If sigma is an alphabet, the same length relation on sigma stars reflexive, symmetric, and transitive. However, shorter than is asymmetric and transitive. And I'll let you verify those. Each of the properties that we've been discussing has a special meaning for that flow of control relation that I talked about earlier, one procedure being able to call another procedure. To say that R is reflexive, for example, is to say that a procedure A can call itself. And this is a common technique in recursive programming. The quick sort algorithm, for example, is recursive. The procedure calls itself. To say that R is symmetric is to say that if A can call B, then B can call A. That's not too common, I think. I mean, it certainly can be true, but just because A can call B doesn't mean that B can call A. It depends on the type of code, type of programming language. To say that R is anti-symmetric is to say that if A can call B and B can call A, then they have to be the same subroutine. So, and finally, if R is symmetric, that means that if A can, asymmetric, sorry, that means if A can call B, then B cannot call A. I've never seen a case of that specifically. But then again, I'm not a professional computer programmer. The two most important types of binary relations by far are the ones that are reflexive, symmetric, and transitive, such as equality, congruence, mod K, and also reflexive, anti-symmetric, and transitive, such as less than or equal to, or the subset relation. Okay. Binary relations that satisfy one here, reflexive, symmetric, and transitive, are called equivalence relations. They are very close to equality. They are candidates for equality. And I'm going to the next video will discuss that, the equivalence relations in some detail. Binary relations that satisfy the second group, reflexive, anti-symmetric, and transitive, are called partial orders. And the theory of order is extremely important in mathematics. It has kind of a bad rap, unfortunately, but we'll spend some time in a subsequent section studying partial order. One more topic that I want to cover, because it can be quite important in certain circumstances, is called the transitive closure of a relation. And to begin, we need just a tiny bit more notation. If R is a binary relation on a set A, the notation ARBRC is shorthand for ARB and BRC. So you've seen this type of notation before. This one, A less than or equal to B less than or equal to C. So that is shorthand for A less than or equal to B and B less than or equal to C. Now, one thing to note is that ARBRC does not imply ARC unless the relation is transitive. It may, in some cases, for some elements A, B, and C, but in general, it will not unless the relation is transitive. In fact, that's precisely the definition of transitivity, isn't it? That for all elements A, B, and C in the underlying set, ARBRC implies ARC. And we can extend this notation to multiple applications of R, more than two. This is a chain of relations. A1 related to A2, A2 related to A3, and so on, all the way up to AN minus 1 related to AN. So here's a simple example. Okay. Now, to motivate the transitive closure, let's look at the flow of control relation again. We'll call it R. Given a program that contains subroutines, we can define a binary relation R transpose, R closure, or it's a transitive closure. I spent so much time writing about linear algebra that I look at a superscript T and I think transpose automatically. This R super T is the transitive closure, as we'll see in a minute, of R. It's got nothing to do with transposes. This is defined by saying that A, R, T, B, if control or execution can eventually pass from A to B. In other words, A may not be able to call B directly, but there's a chain of subroutines, A1, A2, up to AN, so that this chain is true. A is related to A1, which is related to A2, and so on, all the way to AN, which is finally related to B. So there's a chain of relations that connects A and B. So it starts with A and ends with B. Each subroutine can call the next one in order. The flow of control relation need not be transitive in general. A may be able to call B and B may be able to call C, but that does not imply that A can call C necessarily. Not directly, but the relation R superscript T is transitive, because if A can call B through the intermediary subroutines, so it looks like this, and B can call C through intermediate subroutines, we can stick these two chains together at the end, the end here and the beginning here, they're the same. So we get to the end here, we just pick up the next chain, we go all the way from A to C. So this relation, R super T, is transitive. In fact, it's the smallest transitive relation that contains the original relation R. Okay. Another way to say contains is ARB implies ARTB. So R super T is the answer to the question, what do we absolutely need to augment R? What do we have to do to R in order to make the resulting relation transitive? The least amount that we have to do to get a transitive relation. What we have to do is connect these chains beginning to end. Okay. So this is called the transitive closure of R. It's the smallest relation containing R that is transitive. And if you hearken back to, I guess, the previous video, when I first mentioned that you can take intersections, unions, and complements of relations, one of its main uses was to find the smallest or largest relation with a certain property. Here is a perfect example. So, in fact, the transitive closure could be defined as the intersection of all the transitive relations that contain R, because the intersection of transitive relations is transitive. That tells us that the transitive closure exists without telling us how to construct it. This tells us how to construct it, but it's not so easy to do. Okay. Here's the formal definition. Let R be a binary relation on a set A, then the transitive closure RT of R is defined by specifying that ARTB if there's a finite sequence of elements of A for which we have this chain of relations. If R is already transitive, then its transitive closure is equal to R. Relations that aren't transitive can sometimes be nasty to work with, and so there are many occasions where if you can get away with it, you will work with the transitive closure of R instead of R itself. Then you have nicer behavior, better behavior. We can describe the transitive closure of a relation on a finite set in terms of its graph. So just to illustrate, let's take a look at this graph here of a relation. This relation is not transitive since V1 is related to V2 and V2 is related to V3, but V1 is not related to V3. Okay? Put another way, in terms of the graph itself, there is a directed path. A path is just a sequence of arcs that are connected to each other. And a directed path means that all the arcs point in the same direction. For directed graphs, ordinary paths are not interesting. Directed paths are interesting. So we can say the one reason this graph is not the graph of a transitive relation, I'll just call it a transitive graph, is because there is a directed path of length 2, and this path is not short-circuited. A short circuit would go from V1 to V3. That's an electrical term, and this doesn't quite fit. A short circuit is a circuit that well, it does in a way fit, I guess. It's where wires are touching when they're not supposed to be, and current is flowing where it's not supposed to flow. So you could think of this as a short circuit. If you think of this direction of arrow as actually flow of current, then another arc from V1 to V3 would short circuit this path. So in order to produce the transitive closure of a relation, what we have to do is include enough arcs in the graph to short circuit every directed path. But keep in mind that every time we include a new arc to short circuit a path, we may create new paths. And so those may have to be short-circuited. They may not, but they may have to be short-circuited. So it's not as simple a process as it might sound at first. And that's a hint that finding the transitive closure of a relation in some concrete way can be extremely difficult. That is to say, finding a description beyond the definition. Okay. Well, let's take a more complete look at Boolean operations on binary relations. The complement, RC, of a binary relation R is simply given by A, RC, B, if and only if not A, R, B. So the complement of the relation of equality is equal to, its complement is not equal to. The complement of the relation less than or equal to is greater than. Okay. Not greater than or equal to. And the complement of logically applies is does not logically imply. So that's all pretty straightforward. Union and intersection looks like this. If R and S are relations, then A is related to B by R union S, if and only if either ARB or ASB. For intersection, it must be ARB and ASB. So the union of the relations less than and equal to is less than or equal to. The intersection is empty because you cannot have two real numbers that are both, one is less than the other, and yet they're both equal. That makes no sense. This isn't a very meaningful example. This one is, however. So just for convenience, readability, we'll let C sub k denote congruence modulo k. And consider C3, congruence modulo 3, and C5. If M is related to N via the intersection of these two, C3 and C5, that means, that's true if and only if, M is congruent to N mod 3 and M is congruent to N mod 5, which means that 3 divides the difference and 5 divides the difference. Well, 3 and 5 are relatively prime, and so if both 3 and 5 divide any number, that means their product 15 will divide the number, and conversely. So M is related to N if and only if 15 divides the difference. In other words, M is congruent to 15 mod N. So M is congruent to N mod 3 and M is congruent to N mod 5 if and only if M is congruent to N mod 15. Now, if we change the congruences, congruence mod 6 and mod 8, we get a little different story. Starts out the same. M is related to N via the intersection if and only if both 6 and 8 divide the difference. But 6 and 8 divide the difference if and only if their least common multiple, 24, divides the difference. So this is the general statement here. M is related to N by the intersection, congruence mod K intersect congruence mod J, if and only if M is congruent to N mod the least common multiple of K and J. This works when K and J are relatively prime and when they're not. When K and J are relatively prime, the least common multiple is the product. Okay, so this formula is worth thinking about. I wouldn't spend a whole lot of time memorizing it unless you like doing that kind of stuff, but it's something you want somewhere in the middle of your mind in case it should come up. Okay. And you should also give some thought to the union. What can we say about the union of congruence mod K and congruence mod J? Well, that completes this section. The next section, which starts somewhere is on equivalence relations. So thank you for watching, and I hope I will see you in the next video.